Okay, mistake in the last video. Not gonna go back and redo it just for the last one, but that was a mistake. Okay, it wasn't 7. Wasn't 70. That math don't math, man. That's gonna be 68 over 100, which is 32 over 50, which is 17 out of 25. Okay, it's right now. Wasn't before. All right. Lesson 4. Conditional probability. Okay. Conditional probability, if it would zoom, is the probability an event will occur given something else has already happened. So there's a condition built into this, right? Some of you might get an allowance. The allowance is dependent on if you did the thing. I will give you $10 a week if you do your chores. If you don't do your chores, I'm not going to give you $10. Independent events, when the event that already happened doesn't affect the probability of a new event. So that's like flipping a coin. Okay, doesn't matter how many times I flip a coin. Coin doesn't remember. Coin doesn't have a history or a browser history to clear. And we read this little bar as given. So this is read as the probability of A given B. Okay, again, don't get lost in formulas. The dependent event, it does affect. Okay, the second event depends on the first to do a thing. I need you to do this, but before that I needed this to happen. Okay, they have to flow with each other. And do not get lost in the formulas. We're probably never going to use them. So let's use some independent examples here, but they don't affect each other. What's the probability of a red cube and a white cube, both numbered 1 through 6, landing on 3, if you know that the white cube landed on 3? Okay. Well, if the white one is already 3, if I know that, I roll them and the white cube is 3, what's the probability that the other one is 3? The red cube don't care about the white cube. The red cube still has 6 sample spaces, totally possible, 1, 2, 3, 4, 5, 6, and only one of those outcomes was a 3. So 1 out of 6. Doesn't matter what the other cube is doing. What's the probability of both cubes landing on odd numbers if you know that the white cube landed on 3? Again, red die don't care what the white cube did. There are 3 odd numbers for the red cube, so a half. What's the probability of a penny, a dime, and a quarter all landing on tails if you know the quarter and the penny landed on tails? Okay, well, the other coins don't care, right? Great for the other coins, they're already tails. What's the third coin doing? The third coin is going to be 1/2. Got half a chance to land on tails. What is the probability of all 3 coins landing on tails if you know the quarter? Okay, so now I got 2 coins. The quarter landed on tails, great. But the penny has a half of a chance, and the dime has a half of a chance. These depend on each other and need to multiply. 1 times 1 is 1, 2 times 2 is 4, 1/4 of the time. Okay. Students responding to a poll were asked whether they were for or against or had no opinion about a proposal to increase funding for a school's football program. And this table is already filled in for you with all of those who were for it, against it, didn't care, and if they were juniors or seniors. See, this is much better, okay, than 11th grade and 12th grade. Those letters throw me off. Juniors and seniors. Makes sense to me. What is the probability that a randomly selected student would be for the proposal given that the student was a senior? Okay. So with these ones, it's important to note that the given will always be our denominator. The given will always be our denominator. And then the numerator is generally what we want. Okay, so with that in mind, what is the probability a randomly selected student would be for the proposal if I know they were a senior? Okay, how many seniors were there total? How many total seniors we got? $45 total seniors. Given that they are a senior, boom. Now, of those seniors, how many were for it? 10. 2/9. 2/9. Okay. What's the probability a randomly selected student would be a junior given that they were for it. Okay, how many people were for it? For it. Looks like 50 kiddos were for it. And then what did I want? They were juniors? Yeah, of these 50, how many are juniors? 40. Looks like the juniors really wanted to improve. What is the probability a randomly selected student would not care, have no opinion, they don't give any kind of F's, given that the student was a junior? Okay, given that they were a junior. Man, I was really hoping it'd be the same thing. I know, right? Fine, I'll do it again. I'll highlight something else. What color do I want? Oh, that's a nice color. Okay, given that they are juniors, how many total juniors we got? 55 total juniors were asked. Okay, given that they were a junior. Of those juniors, how many didn't care? 10. All right. And lastly, we have a Venn diagram. It shows some 10th graders. It shows the number of high school students that have a computer, and that's it. So either you are a 10th grader and you are here, or you have a computer and you're here, and this number represents kids who are not 10th graders and don't have computers. Find the probability of A given B. Okay, well, how many B's do we have total? It's not 45, it's 60. Okay, now of those 60, how many are also A? The 15, that's where the overlap is. Explain what the probability of A given B represents in the context of the problem. It's just saying how many of those computer havers were 10th graders. How many of those 10th grades have computers? It's 15 of them. Find the probability of B given A. So, probability of B given A. How many are in A? 35. Of those 35 in A, how many also happen to be in B? Well, it's still 15. So 3/7. Was that 10 ever relevant at any point in time? No, it wasn't. Why was it there? To confuse you. Because I'm mean. Okay, I think that's it. Yeah, there you go. That's the whole thing. Congratulations. You've probability.